All right, so we're talking about secure coding, and in this one, there's a couple of sections here. Uh, the most one where most people seem to spend most time is where you write deliberately vulnerable code and then you have to patch it. And if you want to be able to get flags to put in the scoring engine on this, which you may not care about, but sometimes my students do and such, then you have to have a cloud machine. And so I made a Google Cloud machine. It has, to be fair, all you have to have is a machine that can be loaded from the internet. You have to have a server that can be reached from the internet. So in principle, you could do it on your home server if you configure port forwarding on your router. So that's one way to do it. But the simplest way to do it is have a cloud machine. So I've got a cloud Debian machine here, and I have a command line giving me access to that machine. So it's a Debian machine. I spelled it wrong when I created the machine, but that's what it is. And so the first couple of projects you have to do is set up your server. So here are just instructions how to make a free Google Cloud server, uh, which works fine, and you get a lot of free service. You could use Azure or anything else too. And then once you've got a server, then you can make it a PHP server by just executing a few commands. You install Apache, and then you install. Oh, that's not the right one. It is. Let me get the right. This is it. Okay. Then you just install PHP, Live Apache, PHP CLI, and do a2nmod to enable the PHP. And then you make the usual PHP test page people like phpinfo.php. And you may have to open the firewall depending on how you set up your Google Cloud account. It may be blocking port 80 and 443. And then once you're in, you'll be able to open the web page and see this PHP configuration page, which, by the way, is a moderate security vulnerability to leave this page vulnerable because it exposes your environment variables. And a lot of people put secrets in environment variables on web servers. So it's not a best practice to have this available on a public server, but it is an easy way to show if your PHP is working. And you can also display errors on your PHP if you like and see those error messages. I didn't do that, but you can. Anyway, once you have a web server going, then you can do a series of these projects where you, let me close some of these extra tabs, where you make a vulnerable page and then patch the vulnerability. So the first one, probably the most famous one, the first one anybody would think of is cross-site scripting. So my Google web server page is here, and let me go to the Google configuration page and show you how that works. Yeah, so here's the VM instances. I've created a default machine, which is Debian 12, I think, headless, and it has an internal IP starting with 10 and an external IP, mine starting with 34. So if you just go to that address after installing Apache, you can open a web page there. And so here's a non-secure HTTP web page there. And I've created this page, which is a small modification of this. You make an HTML form, and this form takes one parameter called name, and it feeds it into a PHP script, and then you make the PHP script. This is very simple coding. And so the PHP script just takes the request called name, and it just prints it out, hello name. So this just takes data from the user and echoes it back. And I made a page here that just demonstrates all three stages of this on one page. So the point is, let me copy that. All right. If you put in a name like Sam and submit, it just says hello, Sam. But if you put in JavaScript like this, script, alert script, and submit, then it executes the JavaScript. So this is cross-site scripting. You're able to add active scripting where it ought to be just static text, and therefore you're able to attack other users. And this is famous for doing things like you paste it on something like Facebook or MySpace, and then everybody that views your page, it runs scripts on their machine and takes actions they didn't intend, like making you their friend or purchasing a product or something. So to prevent this, there's a couple of defenses. The first one, the simplest defense, is to get rid of the less than and greater than signs. You can just remove them. And you can use the string replace function in PHP to do that. So in that case, if you just remove them and submit it, now your name turns into script alert1 script without the less than and greater than signs. So it does fix the problem. And the scripts don't run, but it's not the most elegant solution to the problem. The most elegant solution is to replace these characters, which have a special meaning in a web page, with these HTML encoded entities that have the same appearance but no longer have that special meaning. And if you do that and you send this, then you will get less than script greater than. You'll get exactly what you put in, except it no longer is treated as control characters inside the page, so the script doesn't run. That's considered the best defense. It's called output encoding. Anything that goes back to the user, you should encode all the special characters so that it doesn't run any unexpected code. And this is, again, the same thing I said all during the exploit development project we did yesterday. The fundamental flaw we're exploiting everywhere is that somehow input that came from the user that was just supposed to be data is somehow misunderstood as active code and run on the server. That's what all these attacks are doing, tricking the machine into running code that was just supposed to be data. All right, and so that's the cross-site scripting. And if you want to get flags, you go to a page here and you feed in the name of your script. I think I've got this ready somewhere. Yeah, here's where you go to flags. So you put in the URL to your public PHP script, and it'll check it. The first grading script will check to make sure that it is vulnerable, that less than and greater signs go there, and they are accepted. The next one will make sure that less than and greater than signs vanish, and the third one will make sure that less than and greater signs are replaced by the encoded form. So this is just a little vuln scanner, you could call it. It sends these simple attacks to your page and verifies if you fixed it. And I have a whole series of ones like this that have the popular flaws. This is shellcode injection, where you take an IP address and then you perform a ping. The same one. In fact, when I did this, someone was asking how hard is it to set up, and here's exact instructions how to set up pages with some of these simple vulnerabilities. So here you have a ping vulnerability, and then the first way to deal with it is to remove bad characters. And by removing characters like semicolon and pipe, so you can't easily add another command after the ping. And the better fix is to allow only good characters. So first you try to remove certain characters that are essential for the attack, and the problem is creative pen testers will often find some way to encode those bad characters so your bad character filter does not recognize them. That's very common. So this is called deny listing. What's much better is to have allow listing, where you only allow good characters, so you don't allow anything except numbers and dots. And if you want to get fancy, you could even have a regular expression that only allows correctly formatted IP addresses. So numbers can't go above 255 or be longer than 4 digits and things like that. That might be even a little better. But from a security point of view, it's probably sufficient to just allow only numbers and dots. There's not much you can do with just numbers and dots to hack into the machine. So anyway, there's a lot of these in the same vein. This one here, you have SQL injection. We talked about before, it's running a server. And you'll install MySQL here and have a page, and then you can see that it's vulnerable to SQL injection for the same reason. That's database functionality. Now, if you put an apostrophe in it, you'll get a syntax error. And that's just like you saw before. That indicates that you have confused it. The apostrophe is treated as something from the developer instead of data from the user. And now you have to put in this kind of thing, which will actually fetch data. And so then you can fix it. And I think the first fix is to filter out apostrophes, which will block the most common SQL injections. But if you have a numerical field, you can do a SQL injection without an apostrophe. So the correct fix is to switch to parameterized queries like this, where the data that comes in from the user is fed into a field here. This is vulnerable code, where you take the name field directly from the user and put it in between apostrophes. So if there's a name apostrophe in the name, it'll be mixed in with the apostrophe in the developer. The fixed code takes a few more lines, but it's like this, where name equals question mark, and you bind a parameter of name into there. This adds that as a data entry here, but it is not in a line of code that's parsed, matching apostrophes, so there's no way for the data item to be misunderstood as a command anymore. This is considered a perfect solution. Nobody's ever found a way to do SQL injection after you make those proper parameterized queries. And here's local file inclusion. This is one of the famous flaws in PHP. It's easy to make a page. They'll go to different pages here. You put in buy, sell, and help, and then it will load these different pages. based on that. So you make a separate page called Buy, Sell, and Help, and it will um, show you that page. This is quite common in PHP that you have a form that takes a parameter, and then that parameter is actually the name of a file. And therefore, it has an obvious flaw that you can put in a name to a different file. So you can put in something like this, dot, dot, slash, dot, dot, slash, dot, dot, slash, ets password, and then you'll see that page. So since you let the user control something that was treated as the name of a file, then they can refer to a file you didn't expect them to refer to. And this is very common in PHP. So again, you can fix it by removing dot dot slash, which will stop the simple attack, but there are a bunch of ways to conceal a dot dot slash to re-encode it or something. And so the better fix is to use a function called the real path that will check whatever comes in to find out what directory it's really going to, and then only allow it if it's going to the directory you want to be exposed and nowhere else. That's considered a much stronger defense. So they're all like this. And the next one is hard-coded secrets. We've talked about this a lot. A lot of people write code and they embed a password in the code. So here it's going to check to see if the password is right, and the correct password is just right there in the code. This is a terrible policy, both because often your source code, which shouldn't be visible, does become visible, either due to an error in the web server. For example, IIS had a vulnerability where you could just put something like $data at the end of a URL and it would show you the source code for a page. And also, people often take pages and then put them on GitHub and send the source code public without realizing there's secrets in the source code. There's various ways it can leak out. And the other problem is, suppose you want to change that password someday because it's just part of your compliance requirements or you're afraid it got leaked. If you just put it in the source code all over the place, it's very hard to correctly update it so things still work. Whereas if you had it in one central repository of secrets in a special folder or file which is the right way to do it, then you'd have one place to update it. All right. And so that's a problem with hard-coded passwords. And once you've got it, then I see the better solution is to store it in an environment variable. This is recommended, although as I mentioned, that PHP info page will leak it out. And that's the only fix I put on that one. And then there's integer overflows, which we talked about before. So you have you're going to take a name. I'm going to make a C function that processes a name. And then I'm going to have a function here that will always return a string of 10 characters or less. It will refuse to take anything longer than 10. That's the idea. And that's because it's right here. If length is greater than 10, print too long and exit. All right. So you can make an HTML form and you can make a PHP script which takes the name and checks the string length. All right, anyway, I'm trying to get the point is to test your form. This will make sure the short name goes in the form, okay? These are unchanged, and if you put in a longer name, it gets rejected. That's the goal here. So you can test your form, and that will happen. That's the expected functionality. However, now, if you give it a very long name, what happens is the name is so long, it exceeds the maximum length and wraps around, an integer overflow. And that's going to be because the length of the name is put in, I think, a short integer here. Let me go to my C script again. Yeah, here. Yes, I define an 8. This length is an 8-bit integer, so it only goes up to 255. So if you make a link that's like a name that's like 256 or 257, it will wrap around and think that's only 1 or 2 characters long. So even though you can't inject a length greater than 10, you can inject that by putting in 255 plus a small number. That's the integer overflow vulnerability here. And so first you have to verify that your form is having that property, that it takes short names, it rejects long names, but it allows very long names. That's the first thing. And then you can feed an overflow. All right. And see that exceeding 255, it gets in there. So again, you have to fix this, modify your C code so that it won't fall for this anymore, and verify that it's been fixed. So that lets people practice fixing these little problems one at a time. And then I've got a series of projects where you actually install a realistic application. Like the OWASP Juice Shop. Juice Shop is a modern app with many files and many folders, and you can run various scanners on it. And really, these things are hard to set up, and the results are quite disappointing for most of them. I found SNCC to be the best, but all of them to be very disappointing compared to the commercial scanners that cost money. There's a few things I haven't included here that I'd like to add. You can do some simple scans with Nmap, and you can do some scans with burp itself. Burp has some degree of a vulnerability scanner, so I'd like to try those and see if they're better. Um, but in my consulting, where people use private scanners, like I think it's Checkmarx. Checkmarx is the static code scanner that they use, and it is much better than any of these free things. It scans very thoroughly. It gives you a really nice report with good recommendations of how to fix code. And there's an active one too. That's for static code scanning. And they also have an active code scanning they use, one of the standard ones. I may remember the name eventually. But the commercial products that cost money are vastly superior to these things. Anyway, um, there's static testing and dynamic testing with free products. But given the time limitation, I wouldn't really recommend trying to set up and get these things going, especially since the results are pretty disappointing. But the manual repairing is pretty nice. And that's a skill you need, even if you use these automated scanners. All the automated scanner is going to do is say, yes, you have SQL injection, and then you're going to have to use one of these procedures to fix it. So, in my opinion, any coder that wants to write secure code needs to know the fixes for like the top 5 or 10 flaws. So that's what I wanted to show you there.